Welcome everyone to the first Coffee with Kalefi of 2023. We are going to start off with a topic that's proven to have struck a nerve, I think, and I don't know if it's a skilled labor gap thing or what the case is, but this may be one of the biggest Coffee with Kalefis that we've had by registration ever, so that's great. So today we're going to be talking about troubleshooting hydronic systems. This is going to be a part two. Part one set of webinars that John Siegenthaler is going to present. So it'll be a month from today in March that we're going to have part two. So I'll go through a couple of the opening slides and I'll turn it over to John. If you have issues with GoToWebinar, best case scenario, just log out and log back in. That usually fixes it quicker than trying to call tech support or anything like that. We will have copies of the presentations and it'll be archived on YouTube as well. If you want a certificate of attendance, we can send those to you as well. So you can get one PDH, depends on your jurisdiction if they allow those to be submitted, but we can definitely provide you with the certificate. So the conversation today is going to be really closely tied to Hydronics 32, which is out now. If you sign up to receive those in the mail, you should have received that the last week or so. And it is covering troubleshooting in hydronic systems in great detail in paper. So we're going to kind of walk through that over the next 2 months with Coffee with Kalefi. You can always see these on the next slide. I think we've got digital versions as well. So you can sign up for a hard copy. You can go to hydronics.kalefi.com, see an interactive version that we can add videos to and things like that. Or you can even download a PDF. So kind of 3 ways to get the information. With that, I'm going to turn it over to our host today, John Siegenthaler, and he's going to walk us through troubleshooting hydronic systems part 1. Over to you, John.
Well, thanks, Max, and thanks for providing such a great audience today. As Max was saying, we're going to be taking a look at troubleshooting, which obviously experience helps with troubleshooting. And when we put this issue together, we asked the question, how do you take a new technician, perhaps somebody that's not familiar at all with hydronics, and teach them to go into a mechanical room, look at a hydronic system and figure out what's wrong with that system and how to fix that? That's a tough topic, but we've tried to put together a logical approach towards it. We'll talk about a couple aspects of that approach today, and then we'll follow up in part 2 in March. So today we're going to talk about physical concepts that aid in troubleshooting, understanding the fundamental physics, the thermal physics, the hydraulic physics that's going on. You can't go around, you can't somehow sidestep the basic physics. And for a technician that understands that can really help them zoom in on a problem faster than perhaps just taking guesses. We're going to look at a step-by-step process, basically starting with where's the fuel coming from, working through what is the system supposed to do when it's working correctly, and then try to identify step by step in the process of converting fuel or some energy source into heat and ultimately delivering that heat to a space. It's a step-by-step process. So where does that process break down? And oftentimes that's where the problem lies. We don't want to go into troubleshooting with the idea that we just make random guesses. And we've seen that. I'm probably guilty of that in the past as well. We don't want to make random guesses. We want to try to take it in a logical manner. And again, assumptions would be just really another form of making a guess. And as I say, we're going to start with energy supply. That's the beginning point of any hydronic system. And we're going to end with energy delivery. Now, in part 2, coming up a month from today, we're going to look at what I call classic causes of compromised performance. We're not trying to troubleshoot a specific boiler or specific make and model. That's really up to the manufacturer, but there's a whole range of generic issues that can come up regardless of the hardware that's used. Things like lack of hydraulic separation or air in a system or corrosion in a system. So we're going to look at several of those, and we've organized this into what are the symptoms when you go in, just like going to a medical exam. A doctor is going to look at what are the symptoms being exhibited, And then what are the possible causes? And oftentimes there's multiple causes for a given symptom. What are the things you should be checking? Should it be a temperature? Should it be a pressure? Should it be a valve setting? And then what are the potential corrective actions? And notice that these things are all in plural. You could have multiple symptoms, multiple causes, definitely several things to check, and there could be definitely more than one corrective action to correct that. And then we'll finish up with some complete systems that have embedded problems. And we'll look at schematics, and some of them are design issues and some of them are operational issues. But by the time we're done with part 2, hopefully you'll have a good understanding and a good approach towards troubleshooting. So let's start off with these physical concepts. And the first one that I'd like to talk about is called thermal equilibrium. What does a hydronic system try to do naturally? Well, it seeks to operate at a condition that is such that the energy input by the heat source is balanced by the energy output of the heat emitters. Nature likes balance, and a hydronic system is certainly a good example of that. If it weren't for controls, if we just turned on a hydronic system and let it find its own balance point, we may have conditions that are acceptable, or we may not have acceptable conditions based on comfort, based on safety of operation, and so forth. Thermodynamics really doesn't care about that. It just cares about that balance between energy input and energy output. And let's start off with a pretty simple example here. We've got a heat source. I'm showing it over here. It could be a boiler, it could be a heat pump. It doesn't really matter. It's something that is generating 20,000 BTUs per hour and adding that to a stream of water. And out here, we've got 31 feet of fin tube baseboard, let's say a residential baseboard. And let's say we take all the controls off the system. We don't have a high limit control. We don't have anything that could potentially interrupt this natural process of the system finding an energy balance. Well, once that system stabilizes, it would stabilize at a supply temperature of about 180 degrees Fahrenheit. Even if we put a limit control back on the boiler and we set that limit control for 200 or even 220, the system isn't going to go above 180. It doesn't have to. And the reason is, at 180 degree supply temperature, this 31 feet of baseboard can dissipate 20,000 BTUs per hour, the same as what the heat source is putting in. So there's no reason for the system to go higher. And that's an important concept, because sometimes a technician might try to set that high limit on the heat source higher and wonder, why doesn't the heat source get there? If there's something wrong with the heat source. And in reality, no, there's nothing wrong with the heat source. The system just found its natural balance point, okay? Now, let's change the system. Let's go from 31 feet of baseboard to 111 feet of baseboard, all right? And let's leave the temperature setting on the upper limit control at 200 degrees Fahrenheit. So let's say the technician still thinks we can get that heat source up to 200 degrees Fahrenheit. We turn the system on. Again, we're putting 20,000 BTUs per hour into the water. With 111 feet of baseboard, we're dissipating 20,000 BTUs per hour, but our supply temperature only goes up to 120. It won't go to 125, it won't go to 130, it certainly won't go to 200. The reason, again, the system has found that natural balance point. It's found its thermal equilibrium between the rate of heat input and the rate of heat dissipation. So again, from a troubleshooting standpoint, understanding that if a temperature isn't going higher just because you set a control setting higher, there's a reason for that. And typically the reason is it doesn't have to go higher in order to achieve a balance. And remember, every hydronic system is trying to find this balance, whether it's a really simple system like this or a complicated system. It's always trying to find that balance. And the other thing to keep in mind is that controllers can interrupt the process of that system seeking thermal equilibrium. For example, if we put the temperature controller on this system and we set it at 160, the system would keep heating up, the temperature would rise, and once we get up to 160, that limit control would click off. The process was on its way towards 180 degrees, but the controller intervened. It shut off the system before thermal equilibrium could be achieved. That's not a bad thing. In fact, imagine if we had decreased this baseboard to, let's say, 10 feet, and if we didn't have an upper limit control on there, and assuming we've got a pressurized system, the temperature in that system could rise maybe 250, 260, maybe even higher. Those are dangerously high temperatures. So the fact that a control would intervene and shut the system off, shut the heat source off prior to the system reaching thermal equilibrium is a good thing. And there are many systems out there that without a high limit control would likely go to temperatures higher than what is deemed safe. I tend to like temperatures no higher than 200 degrees. If we had a loss of pressurization, we're below the atmospheric boiling point of water, so we aren't going to get a steam flash. But again, take the controls out of the picture, think about thermal equilibrium. Now, the other equilibrium that hydronic systems seek is called hydraulic equilibrium. And it's the same concept. We have circulators that are imparting mechanical energy to the water. We call that mechanical energy head. You know, it's a term that's been around the hydronics industry for a long time. And sometimes people say, well, head is equal to differential pressure. And actually, that's not true. Head is simply a word that describes a form of mechanical energy that a circulator imparts to water. And as that water moves through the system, everything it comes in contact with, even between the molecules of H2O, there's a frictional effect that is dissipating mechanical energy ultimately into heat. It's just like slowing your car down with brakes. Your brakes ultimately convert the kinetic mechanical energy of the car into thermal energy. So again, hydronic systems seek this balance. So circulators add head energy to the fluid. And the evidence that that energy has been added is an increase in pressure. So for example, here we're going in at 12 PSI. We've got an operating circulator. We're injecting this head energy to the fluid, and we're coming out at 18 PSI. We could actually calculate how much head energy in feet of head based on the change in differential pressure, okay? And the way we represent the head added by the circulator is with a pump curve. And you can see a typical pump curve where we're plotting flow rate that is passing through the circulator, and we're plotting that against the head energy that's added. And typically the units in head energy in North America, we use feet of head. And just as a side note, where does that come from? It actually comes from foot-pounds of mechanical energy per pound of fluid passing through the circulator. If you take foot-pounds of energy and divide it by per pound, the units of pounds cancel out and we get just a unit of feet. But one of the practical ways to think about this is the number of foot-pounds of mechanical energy added to each pound of fluid as it's passing through. And you can see it's definitely not a constant. The higher the flow rate, the lower the number of foot-pounds of mechanical energy added to each pound of fluid. So that's the energy input side. Now let's look at the energy dissipation side. Everything that the fluid moves through, fittings, pipes, air separators, dirt separators, valves, everything that there's actually motion of fluid passing through causes dissipation of head energy. The evidence of that dissipation is a drop in pressure. So for example, let's just say we have some collection of pipes and components in this gray box. We're going in at 10 PSI, we're coming out at 7 PSI. That drop in pressure, that delta P of 3 PSI, is the evidence that we have lost some of that head energy. And we represent that for a given hydronic system or circuit with what's called a system head loss curve. Now, this could be for, if it's just a simple one loop system, the term system head loss curve is appropriate, but you could create a head loss curve for each zone circuit in a multi-zone system. So whatever that circuit is, that fluid pathway, as the flow rate through that pathway increases, the head loss goes up. And you can see it is, it's actually a second order curve. It's not a straight line. So the higher the flow rate, the faster the rate that we're dissipating this head energy. So we've looked at head input and head dissipation. Let's put them together. We just plot the two curves on the same graph. The blue curve was the head loss ability of the circuit. The red curve is the head input ability of the circulator. And where they cross is where we have this hydraulic equilibrium. We call that the operating point. It's very useful because if we just drop a line down here, we can read what the flow rate in the system should be. And likewise, we could go over here and get head, and we could convert head to delta P. And actually, if you had a differential pressure gauges, you could actually measure that. So again, understanding that if you're not getting the flow rate that you expect to have, think about how that circulator curve and that system head loss curve interact. And there are several things here that can change that operating point in a system. One is obviously you change to a different circulator. Go to a bigger circulator, you're going to move this pump curve up, and the operating point is going to slide farther up that blue curve. Or you could change the speed setting on the circulator if it's a multi-speed circulator. It's effectively like putting, either going to a higher speed would be like putting a larger circulator in the system. You don't see this much anymore, but in the old days, trimming the circulator's impeller, actually taking the impeller off, putting it on a lathe and trimming it down to try to tune the circulator to a specific flow rate. Today with variable speed pumps, again, you don't see much interest in trimming circulator impellers. Adjusting any valve in the flow path. If we have a balancing valve, even an isolation valve on a circulator, if we partially close that valve, we are changing that system curve. As we close the valve, this blue curve would get steeper and an operating point would move to the left to a lower flow rate. All right. Changing the type of fluid. If we add antifreeze to water, we're going to change the viscosity and the density of that fluid. That is going to have a bearing on that system curve. Higher viscosity is basically going to steepen up the system curve and give us a lower flow rate. Even changing the temperature of the fluid, in theory, has some effect. Cooler fluids are more viscous than warmer fluids. And again, the viscosity does change that system curve. Certainly if we change pipe sizes, okay? So these are all things that could affect that flow rate. And adding or removing components from a flow path. If we add another valve to a system, if we add another heat emitter in a circuit, that is going to affect that system curve, and it's ultimately going to affect where that operating point is. So again, from a troubleshooting standpoint, understanding how the circulator interacts with a piping circuit it's important. And then finally, transient versus steady state operation. Now, when we design hydronic systems, we're usually designing in what I call a snapshot condition. We're making an assumption that the system is operating at steady state conditions at some design load condition, which is usually corresponding to the coldest day of the year. What is our system doing? What is our flow rate? What is our BTU per hour heat transfer rate? So we're designing and selecting components based on this concept that the system would operate hour after hour after hour at some steady state design load condition. And the underlying assumption is that if it can do that, it can maintain comfort in the building regardless of how long that design load condition persists. But in reality, most hydronic systems are seldom operating at steady state conditions. What's happening? Heat source is warming up or cooling off. A thermostat calls for heat, the boiler's cool, it has to warm up. Obviously, the temperature is going to change as it warms up, or after the burner is shut off, it's going to cool down. We could turn zone circuits on or off. When we turn a zone circuit on, we'd have cool water coming back. That is going to change from, if the system was at steady state and we turn another zone on, we are at least temporarily throwing that system into a transient condition. Internal gains in sunlight, people, lights, appliances, anything like that, even variations in fuel or air supply, air fuel ratio going into the combustion system, that can all have a bearing on the heat output, and hence it could cause conditions to change within the system. So really what we're doing is we're troubleshooting a moving target rather than a steady target. And this is just an illustration. Now, when we talk about boiler outlet temperature, we'd like to think that as time goes on, some heat source, some hypothetical heat source maintains some nice set point temperature. In reality, it isn't doing that. The temperature is dropping, the burner's turning on. As we inject heat into the system, the temperature is going up. We get to some upper set point condition. We shut off the burner or shut off the element, whatever's creating the heat. We coast a little higher, and then we kind of repeat that cycle. So you can see, even though we'd like to talk about, oh, the boiler's putting out 180-degree water. Well, no, it might at an instant, but in general, that temperature is varying. So from a troubleshooting standpoint, a temperature measurement made at one moment, it's likely to change up or down. So if you took a reading on a meter and said, oh, the temperature is 170 degrees and the controller on the boiler set for 180, something must be wrong. No, maybe if you wait another couple minutes, the temperature might even go above 180. Okay, so don't necessarily conclude that something is wrong because a measurement you've taken at some instant of time at some location in the system is not exactly what you think it should be. But keep in mind that, and this kind of goes back to thermal equilibrium, if you're watching a temperature in the system going up, it's generally because the rate of heat input is greater than the rate of heat dissipation. The system is moving towards that thermal equilibrium condition, and vice versa. If you're watching a temperature going down, even if the heat source is operating under that whatever condition that system is at, something is taking heat away from that water faster than what your heat source is putting energy into that water, heat into that water. So this does complicate troubleshooting. Troubleshooting would be a lot easier if systems always operated at some fixed steady state condition. Now let's talk about troubleshooting process, okay? Troubleshooting a hydronic system, it's a matter of verifying actually many processes that are supposed to occur in some pre-established sequence and in an expected manner. And I've put down here, start at the fuel supply and trace these various steps all the way through to the level of comfort present in the building, okay? The root cause of that performance issue, it's often discovered when one of the steps in that overall process is lacking or isn't occurring as expected. It's being interrupted or impaired by something. So as you move step by step through the troubleshooting procedure, maybe at step 4, a contact in a relay is supposed to shut and turn on a circulator. Well, the circulator isn't on. Maybe that contact is broken or the device that operates that contact is broken. So that's the idea, step by step. And obviously, sometimes the problem is very apparent. You walk into a mechanical room, you see water spraying out of a boiler. Well, it's pretty obvious that's a problem. It may not be the only problem with the system, but obviously water spraying out of a boiler or smoke coming out of an electrical control is something you got to deal with quickly. And I put down, that's kind of the easy scenario. It's obvious what at least that initial problem is. But oftentimes it's more complicated because the problem is not readily apparent. So now we've got to go to this step-by-step procedure and try to logically trace through what that system is supposed to do until we find something that is supposed to happen that isn't happening. And I put down as a close on this slide, don't always blame the boiler. Oftentimes, homeowners or building owners, if something isn't comfortable in the building, it's the boiler's fault. Well, more times than not, it's actually not the boiler's fault. It's something else in the system. Maybe it's a zone valve or a relay or a plugged filter, or maybe a 4-year-old got in the mechanical room and likes the look of that nice red handle on that valve and has shut it. We've seen this happen. So I'm going to have Max do a poll here. And in this first poll question, I'll read it and then Max will tally it up for us. Which method of training new technicians for troubleshooting hydronic systems do you prefer? Okay, so again, we're aiming Hydronics 32 as a training aid for new technicians, but we're interested in your feedback. How do you train a new technician to troubleshoot hydronic systems?
Well, those answers are coming in, John. Another perceived culprit for a heating system not working is just the thermostat too. That homeowners that don't even know where the mechanical room is in their
Absolutely.
building may think that the round Honeywell thermostat is broken, and that's why they don't have heat. It's something too.
Yeah, yeah. Or dead battery. We're getting there.
Yep. Okay, I'll give this a couple more seconds and then close it out. Okay, so I'm going to share these results. I'll read them for you, Siggy, just so if you can't see those shared. So 60% said ride-alongs, and then 20% said sending technicians to manufacturer training, and then third place would be in-house training, so something that the firm itself conducts. And then the outliers are self-study, and we don't provide training. So we don't provide training. We're glad to see that was the lowest of the votes there. So yeah, I think that's great.
So the ride along by far is the majority here. And again, that's fantastic. If you've got experienced technicians on the job training, I'm a huge believer in that. And I'm glad to see that won out here. Okay. So step one, let's start with what is the system supposed to do when it's operating correctly? We've seen techs go in with a misunderstanding of what is the system supposed to do. You've got to learn what is it supposed to do before you can try to correct why it isn't doing that. And sometimes an owner doesn't really understand that. Sometimes the owner thinks there's a malfunction and it turns out to be not a malfunction. And here's a good example of that. A boiler that is supplying space heating and an indirect water heater, where a controller that is operating the space heating circulator or perhaps multiple zone circulators is also operating this domestic hot water circulator, but it's doing this domestic water circulator as the priority zone. In other words, when that domestic water circulator is on, it's going to turn this circulator off. And perhaps on a very cold day, depending on how long that domestic water call is on, let's say you have 2 or 3 showers happening in a row, or you have laundry, you have a big demand for domestic hot water, that domestic water tank might require heating over at least half an hour. And during that time, perhaps one of the spaces in the building cools down, and the owner assumes, oh, there's something wrong, that space is cooling down. And really, no, there's nothing wrong, because that's the way the system was set up. Now, if that's unacceptable, it's easy to make that domestic hot water circulator have the same priority as the other circulators, but we don't necessarily want to conclude that something is wrong simply because that's the current configuration of the system. So this is where you get to ask lots of questions to the owner. First of all, is there documentation for that system? Hopefully there is. Some of the hydronic systems we've seen over the years are very complex, many pumps, many controls. Hopefully there's a roadmap, but some kind of documentation that lets the new technician look at what is supposed to happen, and hopefully that documentation includes a description of operation. Are thermostat setbacks at specific times? Okay, that could be the cause of a lower than expected comfort condition. Does the problem occur on a regular basis? For example, if we go back to this indirect water heater in the priority zone, let's say in the morning there's 3 or 4 showers taking place, and consistently we notice that bedroom number 3 is a little bit cool when that happens. That's probably a hint that, let's go back and see what's happening in the system on a repeated, consistent basis. That is perhaps the underlying cause there. Ask them, are there any recurring or abnormal noises in the system? Hydronic systems that are operating correctly should be relatively quiet. There'll be some small hum from the circulators and perhaps the heat source, the burner, compressor, but we shouldn't be hearing screeching sounds or popping sounds or banging sounds going on. Okay. What type of maintenance has the system had and who's been doing it? What about power outages, brownouts, voltage drops? Sometimes newer controls are susceptible. Okay. Have any smoke alarms or carbon monoxide alarms been going off? Obviously, a carbon monoxide alarm going off is an urgent hint to take a look at that combustion system. Have there been any recent modifications to the system? Maybe you added a zone, maybe a burner nozzle was changed, maybe a control setting was changed. Are there large domestic hot water draws at certain times of the day? Again, pointing back towards this prioritized control. Here's one that's interesting. Pool chemicals, chlorine, detergents, cleaning supplies, anything that has chlorine in it that's stored in proximity to an atmospheric boiler is a real problem. That chlorine vapor can go into the combustion chamber and create hydrochloric acid, severe corrosion. So you do not want to store pool chemicals, detergents, or cleaning supplies in a mechanical room. And yet I've walked into many mechanical rooms that simply because there's space there and people don't frequent them, that's where the pool chlorine tablets get stored and so forth. Who's had access to the mechanical room other than the owner? Quick true story here. Town hall project, court night. We got a bunch of people standing around in the hall that are a little bit upset because they're there to pay tickets and fines and so forth. And we had a local case here where the mechanical room was left unlocked and one of the disgruntled people went in there and they saw those valves and just started turning the handles on the valves, figuring this'll fix them. And it did. It shut that whole system down for quite a while. So in general, public buildings, you want to have a lock on a mechanical room. Okay, have the owners seen, smelled, heard anything unusual? Have there been error codes on controls? Have there been trip circuit breakers? So these are all things that are a good starting point, good questions to ask the homeowner that can help zero in on that problem. And I put down here, most owners won't intentionally hold back disclosing information that might help identify the problem. They just don't know something that they've seen, heard, smelled, okay, could be could lead you as a technician to the underlying cause. Now, here's another one. Write down or record, maybe you take photos with your phone, but record all the as found controller settings before you touch any of the controls. It's very easy to start pushing buttons and turning dials on controls, only to figure out 10 minutes later that you didn't write down or record what those settings were. And I've been there and I've done that. I'll be the first to admit it. And sometimes you want to go back to the as found condition, okay? You can actually make problems worse by just arbitrarily starting to adjust controls. So if a controller setting is going to be changed, make sure you record it. What was the as found condition? Why was it changed? What was the new setting? And what is the date and the person who made that change? That's going to help you. It could help a future technician that is trying to troubleshoot the system as well. So documentation of what you're doing, especially when it comes to controls, is really important. Verified electrical power and fuel supply. In the last couple of years, I've had occasion to replace at least 2 circuit breakers that were relatively new, but simply failed. So just because a circuit breaker isn't tripped doesn't mean that you necessarily have power output. You've got to put a meter on there and check that, okay? Just because the fuel gauge on a oil tank shows maybe half a tank of oil, maybe somebody closed this valve, maybe this filter is plugged, okay? You've got to check for fuel supply to make sure that if it's a boiler, that the food that boiler needs is available to it. So filters, valves, and checking power supply. Verify that the thermostats are working, to Max's point. Before we start changing circulators and changing other things in the system, check if the thermostat, first of all, is set for heating mode, if it's a heating cooling thermostat. And assuming you're checking it in the heating mode, check the batteries if the thermostat has batteries in them. We've got a local HVAC firm that advertises that one of their clients paid $200 to have a technician come out and change one of the AA batteries in their thermostat. So obviously check the batteries. Now, if it's a 24-volt rated thermostat and you have an R and a C terminal in the thermostat, put your meter on it, see if you've got a nominal 24 volts. It might be 26 volts, it might be 23 volts, but nominal 24. You can check operation of thermostat, temporarily set it to a high setting, higher than what the room temperature is by several degrees. Say you turn it up to 80 degrees and check to see, do you have 24 volts nominally between the W and the C terminals, okay? We want to make sure that the thermostat is at least giving the electrical contact closure that is a call for heat, all right? And down on the zone relay controller, you can also check down here, basically 24 volts between R and W, between W and C. If there's a call for heat coming into this thermostat, you would have a nominal 24 volts between common and W. If you don't have that voltage there, maybe the wire's broken, maybe something in the thermostat is broken. We've seen sheetrock screws driven right through thermostat cables that would short it out and keep basically the call for heat on perpetually. So basically we're looking for, starting at the thermostat, do we have a legitimate call for heat, and is that call making it down to our zone relay panel? Okay, verify that the heat source is enabled to operate. First of all, do we have line voltage at the heat source? If it's a heat pump, you're looking for typically 240 volts, 230 volts between L1 and L2. If it's a boiler, usually it's going to be 120 volt circuit line and neutral. Check it with your meter. Don't assume because the circuit breaker is closed that you've got it. Now, if you've checked the circuit breaker, you've got line voltage present, but you don't have it at that controller, look at upstream devices. A manual reset high limit is basically a switch that has to be closed for line voltage to get to the high limit control. Low water cutoff, same thing, service switch. Are there other devices in that pathway between the line output from the circuit breaker and where line voltage has to hit the high limit control? Okay, check that there's a closed contact continuity at the XX terminals on the zone relay controller. If you're using zone relay controllers for pumps or for zone valves, typically the XX contact is an isolated contact that closes whenever any zone calls for heat. And if you have continuity across there, in other words, you put your meter on there and you have essentially zero resistance, or you set it and you get a little tone, that means that contact is closed. If you're not getting that, something is wrong with that zone relay controller or upstream of that. In other words, the boiler is not actually receiving the call to operate if you have that type of a setup, okay? Check continuity across the boiler enable terminals of any controller. It might not just be the zone relay controller. You might have a staging controller, you might have other controllers that do multiple functions that are capable of calling the boiler to operate. Check to make sure that the contacts in those other controllers are closed, giving that signal to the boiler to start. And you can simulate a call for heat at the heat source. If it's, you can see here, this is an oil-fired boiler. It's got a pretty simple high limit control on it. Typically, you'll find a couple terminals marked with the letter T, and that was for thermostat. If you put a jumper between TT, you're in effect simulating a call for heat from whatever. It could be a thermostat, it could be some other controller in the system, but if you put that jumper across TT, you verified you've got line voltage available, you're not getting any response. Again, it could be a problem with the high limit controller or something upstream of that, okay? Keep in mind that even if the boiler is enabled, in other words, let's say we've put that jumper on TT and nothing's happening. Well, maybe the water temperature in the boiler is between some high limit setting and some differential that the boiler has to cool down through before that burner will start again. Okay, so just because we've enabled the boiler doesn't guarantee that at that moment that boiler is going to fire. All right, that's why we use the term boiler enable. And when you're dealing with heat pumps, keep in mind, most heat pumps have internal time delay relays, especially if they're switching between heating and cooling mode. But sometimes anytime a heat pump starts, this is a water-to-water geothermal system, the contact that closes to give the go signal to the heat pump, you might see one light come on, but you might have to wait 2 or 3 minutes before the compressor actually starts. Those are built-in time delays, and they're in there to prevent a short cycling problem where a compressor's been on, it shuts off, and then 5 seconds later, it attempts to restart against a high refrigerant pressure. So again, keep that in mind, look at the documentation, make sure that you understand if there's a time delay function built in. Now, looking at the zone relay panels themselves, again, I'm showing one here that has 4 thermostats up here coming down to 4 circulators. First of all, check line voltage. We have line voltage to the controller. If not, something's wrong upstream. Check for any fuses. If you've got little glass fuses or sometimes little circuit breakers that are actually built into the relay panel, make sure that the fuses are not blown. Again, use your meter, do a continuity check. You can simulate a call. Again, if you jump between the R and the W terminals, in effect, you're doing what the thermostat would be doing when it calls for heat. You're providing a circuit path between R and W, okay? Jumper in place between R and W, check to see if you've got line voltage down here at the circulator. Okay, so this is the call for heat. If you're not getting line voltage down here, something is wrong in between. It could be a fuse, it could be a bad relay, but something is wrong in between. So you can see as we're working our way through these steps, we're basically starting with power available, and then we're working through what is supposed to happen. Thermostat calls for heat, zone relay panel responds, turns on a circulator, and so forth. Now, verify that flow is not blocked by air in the system. There's a lot of things that can cause this. One of the classic ones is a circulator that is pumping towards the expansion tank and has a system effect where we're going to negative pressure in parts of the system. We're actually pulling the pressure in some portions of the system below atmospheric pressure. If there's any kind of a float type valve there, air vent, anything that could potentially leak air, that system is trying to suck air in. So, that's one of the things to check. Has the system had a good forced water purging? Okay, here's a typical makeup system. I like to put a ball valve in so we can get the highest possible incoming flow rate to really push that bulk air out of the system when we commission it. Maybe somebody hasn't done that. Maybe they've just opened a valve and assumed that all the air will rise up regardless of whether the piping goes up, down, and so forth. You could have air trapped in the system that way. So forced water purging is a good way to push as much of that bulk air out as possible. Do you hear gurgling in the heat emitters? It's not uncommon at startup, but a good air separator will take care of that over time. Is there a good microbubble air separator in the system? These do a much better job than the old cast iron air scoops do. They will capture that residual dissolved air over a period of a few days and eject it from the system. So again, there's many possible causes that allow air to get in, okay? Improper placement of the expansion tank, low system pressure. If you let the pressure get too low, again, depending on how the circulator and the expansion tank are installed relative to each other, that just sets the stage to create these negative pressures and perhaps suck air back into the system. Lack of backflow preventer along with a building pressure drop. Without a backflow preventer, if the building pressure drops, the expansion tank is basically just going to push water back out, and that could cause a low pressure condition in the system. Clogged screen in the feed water valve, loose valve packings. Here's an example over here where you can see this crusty film on the outside, or flakes on the outside of a valve. That tells me that bonnet is leaking. Here's another one of a flow type air vent where obviously there's been water leaking out of this thing. So or a disabled feed water system. If somebody has shut off that feed water valve, over time that pressure inevitably will go down, and you could get to a condition where air is drawn back into the system or something is causing a blockage of flow. Okay, so let's do one more poll question here. What's the most frequent issue your techs encounter when troubleshooting a hydronic system? That's a pretty broad question, but Max, I'm going to let you, we'll watch how that goes.
Okay, I've got that started there. One of the questions going back to, and we've had a couple come in the chat too while we're waiting for results. You wrote an article at one point about can you just turn up the pump speed to double the amount of BTUs in a zone? And you had an analogy with like horsepower and cars and maximum speed. Yeah. Could you give us kind of the 30-second version of that?
Yeah, the short answer is if you double the pump speed, you will not get double the flow rate. Remember, that system curve goes steeper and steeper as you go to higher flow rates. And a good analogy to it, I think, was with cars. If we had a car with a 100 horsepower engine and we can go 100 miles per hour with that car with the throttle wide open, and let's say you wanted to go 200 miles per hour, like NASCAR speed, could you do it by taking the 100 horsepower up to 200 horsepower? And if you follow NASCAR, you know the answer to that is absolutely not. Those cars are running more like 800 horsepower. So no, you cannot double the BTUs per hour or double the flow rate by increasing the pump speed. Even putting a second pump in will not double that flow rate. And again, you can find all that information if you plot those pump curves and system curves. When you have two pumps in series, you basically double the head at the flow rate. And depending on what the system curve looks like, you will get an increase in flow, but definitely you will not double it.
Great, thanks. Okay,
So what are we looking at?
So it looks like more of an even distribution here, but electrical issues with controllers was 28% of the share, and then plugged strainers, number 2.
Okay. Wow. So yeah, plug strainers is right up there. That's interesting. Yeah. Electrical issues. Yeah. That, today as we put more and more electronic controls into systems, we're likely to see that more, especially if the electrical system in the building doesn't have some type of surge suppression in it. I would recommend that certainly today in any hydronic system with electronic controls, some kind of surge suppression in the system to prevent a brownout or a nearby lightning strike or whatever could cause a voltage transient from damaging those controllers. Okay.
Send it back over.
Attempt to verify the flow rate in each active zone circuit. Now, if you've got a flow indicating device like a quick setter valve here, that's really easy. Just pull the ring and you're going to get a readout on the flow. It gets a little more challenging if you don't have any flow indicating device, although here's one of the things that has come along that is a help. There's several companies now, Taco, Grundfos, and Xylem, all have small circulators with ECM motors that have Bluetooth capability and can communicate with a smartphone, and they can actually show you the flow rate. It's not lab grade flow indication, but it's enough to at least get you in the ballpark. If you're expecting 6 gallons a minute and you're seeing 2 gallons a minute, obviously that there's something inhibiting that flow. If you're seeing 5.5 or 6.5, that could be within the tolerance of the measuring device. But I do appreciate the fact that these circulators can at least give you a reasonable estimate of what that circuit flow rate is. Here's another thing. when you see very large temperature drops in a circuit, it's almost always an indication that the flow rate is too low. So up here at the top, here's a case where we have a tiny little flow rate going in here. We're going through some kind of a circuit and we're going in at 160, we're coming back at 95. So our delta T is 65 degrees. Now that is way beyond what a reasonable hydronic distribution circuit should be operating at. And typically that's the underlying cause of insufficient heat delivery. Something is causing that flow rate to be much lower than it needs to be. Okay, here we've got a flow rate, we've gone up to 1 gallon per minute. We're going in at 160, we're coming out at 146. We've got a delta T of 14, much more reasonable. Okay, and just to show you, I made a plot here. I've had this plot for a while. This is a floor heating circuit. It's 300 feet of 1/2-inch PEX tubing in a 4-inch concrete slab with no covering, 12-inch tube spacing, 100-degree supply water. And I just want to show you the temperature drop of the circuit can vary a lot. If we're doing 2 gallons per minute into that circuit, we're actually a little under a delta T of 10. And then as we decrease flow, you can see the delta T keeps going up. If we got way down here to 0.2, we'd have a delta T of like 35, but maybe 37 degrees Fahrenheit. Again, if you're taking temperature measurements on a floor circuit or even a baseboard circuit, and you're seeing 35 plus degree delta T's, it's almost always indicating insufficient flow. And now it's up to you to go find what is the cause of that insufficient flow. Okay. All right, checking system fluid. This is becoming more and more important in hydronic systems, especially as we get into heat pumps and modulating condensing boilers, where whatever comes out of the tap isn't necessarily good enough to go into that system. Typically, you want to draw a sample into a nice clean glass container. It's common, especially in boiler systems, cast iron boiler systems, steel boilers, that water might have a slight grayish tint to it and a metallic smell. Usually that's not a problem, but if you're seeing like a black syrup come out, that's definitely a problem. If you're smelling something that is foul, if the system has antifreeze in it, that antifreeze is probably degraded thermally, especially solar thermal systems were classic causes of this due to stagnation. That fluid needs to be replaced. So I would recommend that you use a cleaner, and there are other products. There's Fernox, there's Romar, there's Sentinel, there's other products to market. I call these hydronic detergents. They go in and basically clean the inside surface of the system. And we actually did a whole issue of Hydronics, number 18, on fluid quality. It goes into more detail on this, but a good internal cleaning of the system, even a new system, as part of the commissioning process to get the solder flux, to get dirt, insects, whatever pipe gets transported today, gets handled multiple times before it gets fastened into your system, and there's likely going to be dirt or grease or something in that pipe. You want to get that out. You want to demineralize the water. Again, Hydronics 18 talks about the whole process of that. We're basically taking the calcium and magnesium salts out of the water. We're reducing its conductivity, and a simple, inexpensive meter like this, you can test looking for between 10 and 30 parts per million total dissolved solids. That is basically removing these salts from the water, and the chemistry of a demineralized water and antifreeze is excellent. Very hard water and antifreeze, that's not the best chemistry. So demineralizing the water is, I feel, an important step in commissioning any hydronic system today. And if you've got a dirt separator in there, especially with a magnet in it, obviously giving that thing a periodic flush and seeing what comes out. You can see here there's quite a bit of magnetite coming out of that system, especially if it's an older system. Maybe it's an old steam system that's been converted over to hot water. Okay, and add a system stabilizer. That will preserve the pH of that water. Check condition of heat emitters. Here's what we call platelet staple up. Really bad idea. I've seen many examples of this where somebody assumes just putting the tubing next to the floor is good enough, and putting some bubble foil or putting some site-built plates over it. These are just very, very inadequate heat transfer paths. You're just never going to get proper performance for that. If it's a convector, here's one that was in an old school, and you can see it's been in an old school for a while. Pencils, scissors, gum wrappers, whatever is down there on that coil. This one was actually taken in a bar. Maybe I shouldn't be surprised here, but you can see it's been mashed up pretty good. So Obviously, heavy accumulations of debris, dust, and so forth on a fin tube element or a clogged filter in an air handler could be a problem. Here's one of my favorite photos. This is a means of regulating heat output from a radiator. Just throw a wool blanket over it. Certainly anything that obstructs air paths is something you want to check out, okay? Make sure that there's an air pathway in and out of anything that counts on convection. And we're almost done here. When it's not when it's the building, not the heating system. So, you know, we've been talking about potential issues with the heating system, but here's one that actually I learned a lesson on. It was a house. We did a nice radiant floor system for this house, a 2-story house, had an air handler for cooling up in the attic. This ducting was sort of insulated. It wasn't, you know, like R30, it might've been R5. And what was happening is warm air, just due to its buoyancy, would go up into this ducting in the winter. It would lose heat through the air handler, through the ducting. It would become more dense, and then it would fall and actually come out of these ceiling outlets on the first floor. You could actually put your hand up there and feel this cool air, and knowing that the blower wasn't operating. So we had what was called a convective loop going on. And it's just something to be aware of. Maybe you're going to need to put something over that return air in the winter time, or put a damper system in, something that's going to block that path, okay? Now, a classic air leakage situation in a house is at the foundation sill joint. I showed this photo. This is actually spray foam that comes down across the band joist, and it actually goes over the sill and actually finishes up on the foundation. This is good. This is a really good air seal at that joint. Most houses don't have this, okay? So look for those air leakages. A blower door test, certainly that's one way to help find air leakages in buildings, okay? Infrared thermography, you can find heat loss. You can actually find areas where there's moisture trapped as well. So you've got tools available to do the building science, the diagnostics, and perhaps the load is quite a bit higher than what you anticipated or what you assumed when you did a heat load estimate for the building. Can you feel air coming in through the outside receptacles? Okay, now that's it for part 1. In March, we're going to get into these other aspects. These are all covered in Hydronics 32. We'll talk about some physical configurations. And again, I won't repeat everything, but there's a lot of good material coming in part 2 of this. And with that, let's see, I just want to go through a few slides, and Max, I'll have you narrate these and I'll flip them through.
Sure. And then I put in the chat the registration link for part 2. If you want to sign up for the next webinar while you're still here, I've got that link handy. If you want to call and talk to one of the guys on the slide here about a project, that's always helpful too. Some of the questions we get are really specific, and it can help to get into more detail with a person on the phone. So we're happy to do that. And then this is a good one if you're riding to work in the truck or whatever. This podcast series is also just ripped right from the tech support lines. Some of the things that come up all the time, and good ways to start the troubleshooting process there. These are kind of a 5 to 7 minute version of Coffee with Kalefi in a way. So Cody's done a bunch of these, and they're really helpful sometimes at the wholesale counter too. If you just want to go over how a mixing valve works, you don't have a full hour, this is a good resource as well. And then send us your job sites on social media. Some of the cool things that we see out there push us to figure out how we can adapt to the new applications that are happening in real time. And we're also happy to just kind of boost your posts on social media as well, and give you a pat on the back for a job well done. Okay, that takes us to the end. I've got a couple questions that I can ask you, John, if you still have a few minutes.
Sure do.
So one of the questions that we got, a couple different forms of kind of the same question: does your system curve change in an older system? And you covered this a little bit, but why would a system curve change potentially?
Yeah, I could see it changing. Certainly any modification to the system will change it, but I'm thinking if it's an old system with steel pipe, if especially a steam conversion, any accumulation of scale inside the piping will increase that frictional dissipation, and it would steepen that system curve. Any kind of a plug strainer that hasn't been checked perhaps in years would cause that to occur. But yeah, anything that adds resistance, internal resistance to the system will steepen that system curve.
And then let's say in like an old cast iron distribution, cast iron radiator system, you wanted to increase the heat transfer. What are maybe a couple places to start there?
Well, assuming you're going to leave the same radiators in place, I would start with probably a good cleaning of the system. If it was a steam system, it's going to have sludge in it. Just every time a steam system cycles, steam goes up, air goes out, and then when the steam cycle shuts off, air comes back into the system. So you've got iron, you've got water, and you've got oxygen, which means you're going to have corrosion. So a good cleaning would be a good place to start. Again, those companies like Fernox, Romar, and Sentinel, they all make these hydronic detergents. Some of them make very specific descaling chemicals that you can put in, circulate through the system to help clean it up. That's going to help. I can't guarantee that that would restore the original condition, depending on how degraded it was, but I would start with a good cleaning.
We have another question about tools to use. One of the tools that I think is a great one to have handy, and they've come down in price a ton, are thermal cameras. A question specifically was, how do you find a leak in a radiant slab? And then the short answer is cross your fingers. But a little bit more specific would be a thermal camera, and that can be a great way to find some spots where radiators aren't as warm, or to just get a visual of the troubleshooting scenario.
Yeah, so Fluor's got some there. You can get some that hook to your phone now, right? That are like $200-300, something like that. So I remember when they were $25,000 for a decent infrared camera. But two tools that I would definitely have in a toolbox. One is a good multimeter. I've got a Fluke multimeter. I've had it for probably 30 years. The thing is, it just works great. So we check voltage, we check continuity with that. We can check resistance on sensors with it. And then I would also get a good differential temperature measuring device. Again, I've used a Fluke. It's basically two thermocouples, and you can tape those thermocouples on. You can get either individual temperatures on each thermocouple, or you can set it and get a delta T, and they're quite accurate. And that's maybe, again, a couple $100 investment to get good temperature measurement and good electrical multimeter. Would definitely be two tools. And the thermal camera certainly is also a good tool.
You did a project years ago where it was almost like you had to put up your house as collateral to get one of those thermal cameras.
Yeah.
It's like a $40,000 camera or something like that. So yeah, that's changed quite a bit. Another tip with that too is, if you're going to use a thermal camera to measure anything metal, put a little piece of electrical tape or painter's tape, something that's dull, on it, because you can get a weird emissivity reading from shiny copper. Where if you have something dull like the painter's tape, you get a better number there too, if you're doing the thermal.
With the thermocouples too, when you put a thermocouple on, you could tape it on with electrical tape and put a little piece of pipe insulation over it too, just to isolate it from the the air. And that honestly, you can get at least down to 1/10 of a degree Fahrenheit on a thermocouple, a good meter today.
And then a lot of these I feel like are going to be, we'll reach out, anybody who sends in a question will reach out after the fact if we don't get to all of them. A lot of them I think are going to be covered in the webinar next month. The other thing that you mentioned that we could go back to specific to this is, you said, assuming we're not changing the radiators in an old cast iron radiator system or something like that, When are good cases to just say, you know what, we need more surface area of heat emitter in the space, that we just can't, we're not going to get it done anymore with that little radiator in the corner?
Yeah, well, assuming you can't go higher in water temperature, and that's especially true today with heat pumps. With heat pumps, we want to do everything possible to keep the water temperature down. With a boiler, the idea used to be, if you don't get enough heat, you just keep turning up the temperature limit on the boiler. And to some degree, you can get away with that, but if you're operating your heat source at a reasonable temperature, trying to get efficient operation, and you simply can't get the heat output, either the space load that radiator is in is too high for the amount of surface area, or actually it's the same thing. If the radiator's too small for the load, so you'd have to supplement that. There really isn't anything. Probably the easiest thing to do would be to try to reduce the load in the space rather than change the radiator. That could be air leakage around a window or a door. It could be a matter of a couple tubes of caulk to seal up an air leak that might reduce the load to the point where that radiator is adequate. So the weatherization people that come into buildings, I would certainly recommend that you'd have somebody available that is in the weatherization business that you can call on to do an audit on the building and do a blower door test, and at least get a handle on, is this heat loss close to what my estimate is? Especially, if the situation turns confrontational, having something to back you up. Look at, based on the drawings you gave me, this is what our heat load calculation was, but our measured load based on a building weatherization person is way beyond that. So that's another resource to have available, is somebody that has blower doors, has other diagnostic equipment that can help pin down where there may be some hidden energy leaks that are causing that load to be too high, so that radiator, or that whatever that heat emitter is, just simply can't cover it. One that we see a lot, and I'm sure you've seen it, is the plateless staple up. I went through it pretty quick, but the idea of stapling PEX tubing to a subfloor or to the joist and putting some bubble wrap up there, nowheres but North America will you see that. It's just a terrible idea from a heat transfer standpoint. And we've seen it over and over again over the years of just disappointed owners. The floors are just not able to get the space up over maybe 55 or 60 degrees. And those plates are really important. And so is that underfloor insulation. That R value should be at least 10 times what the R value on top of the plates is. You just can't cheat on underfloor insulation and leaving the plates off. So plateless staple up, as I put down, really bad idea. If you walk in and see that, that's very likely to be the cause, especially of inadequate heating in a space.
And that's a good point too. The two things, the energy auditors sometimes are great sources of leads that they come into Weather Seal and they say, you know what, you're in pretty good shape, but the mechanical system looks like it might be ready for an upgrade, and then can pass those over to you and vice versa. There are a lot of boilers, that brand new shiny condensing boilers that have been installed in houses that really should have started by insulating the attic, that aren't going to be set up to be as successful as possible, which is always a shame because everybody wants the boiler condensing really well in those higher energy efficiency points.
Well, energy conservation is the low-hanging fruit, and anything you can do to bring that load down is definitely going to improve not only how much energy is being used, it's going to improve the comfort as well.
It's the boring one, though. I think that's the problem. But just like more insulation in the attic isn't as much fun as the new heat pump or boiler in the mechanical room.
Right.
So you know what I'm gonna do, John? We had that third poll that we didn't have space for. I'm gonna just launch that for the people that are in the room still. So which methods do technicians prefer for gathering information on hydronic system components during troubleshooting? This is also something just for our own information too. We'd like to see what we should put our resources into.
Yeah, so the context here is a technician, he's at a site and he's looking at a component. What's the best way he can get information quickly to determine what that component is supposed to be doing?
Okay, I'm gonna close this one. So we've got a pretty close race between product manuals left on site in first place and then looking up components on cell phones and tablets. So the product manuals on site, as when I worked as a rep in the past, those can be helpful because they should directly line up with that manufacturing date. And if they made some sort of change, 4 years later to that control sequence or something like that, that might not be reflected. So whatever shipped with the equipment is always a good place to start if you can find it, which was one of the comments that we had in the questions as well. And then yeah, a lot more people are using their phones to pull up those documents when they can't be found. So that's good as well.
I'd throw a quick pitch in. We did an issue of hydronics a few years ago, and I don't remember what the number of the issue was, but it was strictly on documenting hydronic systems, and it talked about what kind of documentation you should be leaving with the system. The piping schematic, the electrical, the sequence of operation, as well as the installation operating manuals of the major components. Put it all together in a binder and mount it on the wall where it's readily apparent. That is a huge help for a technician that is coming in that's unfamiliar with the system, especially if it's a complex system. That's a tremendous resource, and it adds value to the system. It's definitely something that has marketing value as well, that perhaps your competitors, if something's wrong, call me, as opposed to, we're providing a complete documentation for your system so it has a long life.
Yeah, that's a great point too, because I think that a lot of complicated systems that are out there now may have had to use some relay magic to get the system to work with the controls that were available. But unless there's some documentation of what I was trying to do here was anybody who takes over the service of that or has to replace a controller that was struck by lightning or something weird like that, you start over, and then the homeowner is the one who pays for you to figure that all out again based on modern control options.
Absolutely. That documentation can save hours in an initial familiarization with the system. And another thing that should be down there, and we do talk about it in that issue of hydronics, there should be a listing of all the initial controller settings. So every controller you have, all the settings should be listed. And again, if you're going to go in and you're going to start changing settings on controllers, make sure you have what those as found settings are, and putting that in documentation can be a real help.
We got a super fan answer that was Hydronics 20 was documenting hydronic systems. So
thank you.
Thank you, Steve. Well, why don't we close it out there? We've got a bunch of questions that could feed right into part 2 that we can pick up with as far as error elimination, error management, things like that. So why don't we call it a day there, and we'll see everyone back in a month for part 2.
Thanks a lot, Max.
Thanks, John.